Hi, my name is Joe Evinger, and I help coordinate the Science and Ideas Group events. I want to thank Hillary Naylor for my co-host for uh, getting us started today. I want to mention up front, there are rolling power outages right now in California, so we have to be ready for that, and any of us could drop out depending on what happens. I welcome all of you to our group. All of our members have varied educational backgrounds, but we all share common interest in science, new ideas. We currently have over 50 members in our group and another 60 on our guest list. We meet via Zoom the second Thursday of every month from 3 o'clock until around 4:30. We have a different guest each month who speaks on a topic related to science and ideas. We rely on our science group members and various members of and committees of Ashby Village to find us new speakers for each month. Besides our presentation today, I'm always actively recruiting for new speakers who might speak to us in the coming months. Next month, we have one of our own members, Roger Newman, who will give us lecture part 3 out of Africa, ancient human dispersals out of Africa. We invite all Ashby Village members to join our group, and anybody in the general public always welcome to join our presentations. But today we are here to welcome our speaker, Steve Self. Steve will speak to us on volcanic super-eruptions and Yellowstone. Steve has been with the Earth and Planetary Science Department at University of California, Berkeley. He studied volcanic rocks in many parts of the world, concentrating on large lava effusions, explosive eruptions, and the impact of volcanism on the atmosphere. His current research includes mechanisms and products of flood basalt and explosive super-eruptions, plus several other projects. He has published and lectured widely on the impact on large-scale volcanic eruptions on the environment and society relative to both our present and future world and path Earth history. Steve lives in Alameda, California, and retired in 2018 from his position as senior geologist volcanologist with the U.S. Nuclear Regulatory Commission. Steve is a fellow of the American Geophysical Union, the Geological Society of America, and the Geological Society, London. With that a long introduction, thank you very much, Steve, for speaking to us once again on a new topic, super eruptions. Take it away.
Okay. How's the sound? Is the sound good?
Yes.
Yes? Okay. Today we're going to talk about the largest scale of explosive volcanism that happens on Earth. And it's very much of what we know versus what we don't know. I try and explain to you why there's a lot of don't knows about this topic, and also put to bed a few myths that I find sort of niggling by looking at the press. The background picture is a picture of the Pinatubo eruption cloud in 1991 in the Philippines. Pinatubo's eruption, and I'll say a little bit about it in this talk, was the second biggest eruption of the 20th century, but tiny compared to the types of events that I'm going to be talking about today. Okay, so now my slides are not changing. Hang on. How do I advance? Okay. Are you still seeing full screen? Can I ask you, are you still seeing full screen?
Yes. Yeah, we're still seeing your share screen with your first slide.
But what about the second slide?
Not yet.
Oh, so what's happening here? Sorry, something we didn't.
There may be a right arrow at the bottom of your keypad. And sometimes if you push that, it will advance to the next.
Yeah, but it's not doing the shared screen one. Let me do this and let me go to, oh God, where are we? Share screen. Let me go to the other one. Try this. And now, this is, sorry for this. It's not changing the slide.
We can see your pointer.
Yeah, bigger. Oh dear. Hang on, second slide. Go to the pointer. There's something happening weird.
Could I just suggest in the lower left-hand corner of your screen,
Yeah.
you find two little arrows, one pointed left, one pointed right,
No.
little carrot-like arrows.
No, I don't. I'm looking for them, but I'm driving it from the PowerPoint to reading here. How tricky is this?
And you tried the keyboard itself, pushing that right.
Yes. Yeah, I've been trying everything I know. Okay, so let me go. It's closed. Share screen is closed. Now let's go to the shared screen again. And well,
Can you see, and if you're in PowerPoint yourself, can you see the individual slides in the left-hand margin?
no, hang on.
I'll be quiet.
No, I'm trying to open the talk again, right?
We've got your desktop.
Yeah. Then I'll just do this. I'll go to share screen. Where do I want to go to increase the size of this? Oh, we didn't have this trouble before, did we?
No.
Stop share, it says now. Stop share. Now I will go to share screen. Now I will go here. And now I will go here and try and make it come up as a display. It won't do it. What can you see now? Can you see,
There
how
we go.
about this?
Ah,
Second slide.
oh,
Yes.
good.
Okay. All right. Let me
Yeah.
see if- yeah, it's going to work. Okay. Oh, sorry for that. This Earth's largest eruptions are all pretty much the same. Okay. They all form calderas, which are large holes in the ground. And you've already mentioned Yellowstone. So we'll say that Yellowstone is an example of a caldera volcano, one of the two biggest in the world. They all form pyroclastic flow deposits. There's a picture here at the top left of a little pyroclastic flow in Onsen, Japan in 1992. And it's come down from the volcano that's in the clouds behind that you cannot see. And it's overrunning farmland and farm buildings and things like this in this picture. So they're very big systems. And in the eruptions I'm talking about, they've become sort of unimaginably big. And also these large explosive eruptions, because they put ash into the atmosphere, they make ash fall deposits. So the wind will blow the plume along and it will spread out, first of all, like this giant umbrella cloud. This is Mount St. Helens on the morning of May 18th, 1980. And this cloud is expanding in the upper atmosphere with a top at about 30 kilometers. So it's much, much higher than jet aircraft fly. And from this will fall ash. And when we go to volcanoes like Yellowstone, as you can see in the bottom right here, we will find the fallout deposits and the flow deposits. And by studying these types of deposits, we can reconstruct old prehistoric explosive eruptions and tell some things about them. I'll be explaining what those things are. In terms of the effect of the natural hazards that these present, these big eruptions are not like other natural hazards that we're more familiar with. We're more familiar with them because they're much more common. Earthquakes and tsunami and hurricanes, perhaps since 2004, the Earth has had some of the most severe of these that Earth can give us. The hazard is over very quickly. We're left with the terrible task of recovery beginning immediately. There may be a few aftershocks for earthquakes or recurring hurricanes, but these hazards, they're very severe. They impact a small to reasonably large area, but you begin the cleanup immediately. A big volcanic eruption would not be like this. There will be a buildup lasting many months to years, and we really don't know how long this buildup is. And the buildup could feature small eruptions from the volcano. There will be a climax to the eruption that could last hours to a few days, and some people even think a week or more. The big explosive eruption in California, Long Valley, down near Mammoth Lakes, that's reputed to have taken about a week before everything was erupted. The ash fallout would last for days to weeks. The atmospheric impact, which I'll talk about a bit later, could last for 4 years. The landscape recovery around the volcano would take decades or much longer. And all of the societal effects of these eruptions are very uncertain, as I'll try and explain. So it's a very different type of much longer term hazard if one of these volcanoes were to become active and heading towards a very large eruption. Oh dear, this has slipped off the screen. There's a word, never mind. The media seems desperate for us to have a major eruption. This is a web page from a few years ago. The Yellowstone supervolcano is the ultimate eruption waiting to happen, right? And it goes on about, you know, how volcanoes are good and bad and everything, but they seem to be, a British newspaper, the Daily Express, seems particularly keen to have us wiped out by particularly Yellowstone. Every year, I mean, this is from earlier this year, they run these articles saying, you know, Yellowstone's pinpoint the first sign of an eruption. They're going to tell us a huge eruption is imminent. And what I want to tell you is the reality of the situation. It isn't like that at all. You know, these eruptions are very, very rare. And Yellowstone is just a super volcano which has had several super eruptions doing its thing, and they do its thing. They do their things for a very long time. So let's take a step back. How do we measure eruptions? We've got all different sizes of volcanic eruptions, and this is just a little bit about how we measure eruptions. Oh dear, back. Okay. Oh, way back in 1982, with a grad student, I published a paper on something called the Volcanic Explosivity Index. This is a rating for explosive volcanic eruptions from 5 to 6, up to 8, even 9, based on the volume of the deposit and also a little bit about the eruptive column heights and things like that. Since then, other people have started using the magnitude of the eruption, which is based on the mass rather than the volume, but that doesn't really matter. But we have a scale, and things like Mount St. Helens 1980 are 5. Also Pinatubo 1991 was a 5. The biggest recent eruption, Tambora 1815 in Indonesia, that was a 6, getting on for a 7. There was an even bigger eruption in 1259 AD of a class 7, also in Indonesia, near to Tambora. And we have to go back a few thousand years to get a bigger eruption, which is the Kikai eruption in Japan about 7,000 years ago. And to get to super eruptions, or the really big size, which are volcanic explosivity index 8 or mass magnitude 8, then we have to go back thousands and tens of thousands of years. Okay, the most recent on Earth that we know about for the big size was one in New Zealand at Taupo volcano 25,000 years ago. And Toba, I'll talk quite a lot about Toba 74,000 years ago. And so they're very, very rare, okay? When you compare even 1,000 years to our sort of standard measured lifetime of approximately 100 years, we're looking at very, very long time scales for these types of events. And not only that, but we haven't had many big eruptions in the past. Here's a little plot from 1800 to year 2000, okay? And it gives volcanic explosivity index VEI 6 and 5. 5 is light blue, 6 is dark blue, right? So in the last 200 years or prior to the beginning of this century, there have only been 2 6s and then roughly, you know, a 5 VEI every few decades. The one in Alaska in 1912, the biggest eruption last century, was very remote, and so its effects were not felt by much. So we have this sort of huge, you know, almost century-long perception gap for big eruptions when nothing happened, and therefore I think they're kind of off our radar screen. There's also, just to add a note, there have been none this century, except there was a strange event at the beginning of the year in Tonga. This is nicknamed HTHH, and it's a very peculiar eruption indeed. And if you want to discuss it at the end, I'm very happy to do so. Oh, this one P here, this is Pinatubo, 1991. This is Krakatoa. Some of you may have heard of Krakatoa, 1883. This is Tambora, 1815. But we've really had, in the past centuries, very few big eruptions. And so it's something that we're really not used to. I showed you a picture of Mount St. Helens eruption column. Here's one from a volcanic event in Chile in 2011. This is a VEI 4. The eruption column was about 15 kilometers height. There's a helicopter here for scale. And you can see this giant umbrella cloud spreading out at the top of the vertical or subvertical part of the eruption. You can't even see the volcano down here. But imagine what this, if this looks this spectacular, then what would something like the 1815 eruption of Tambora be like? It'd be very, very severe indeed. And this rams home the same point, really. Eruptions in the recent past have been tiny, and we're not used to thinking about large-scale eruptions. So this is magma volume here, plotted against some well-known eruptions of the last few thousand years or more, okay? And the most recent super eruption of mass, or VEI 8, is here. This is this one in New Zealand. I told you 26,000 years ago, sorry. And it still looks pitifully small against the biggest ones that we know about, which are immensely huge. And Toba in Indonesia might be an example of this. And we're going to, as I said, we're going to talk about Toba later. This is the same data on a log scale, so you can sort of read off the size of all those that didn't even get off the starting blocks on the previous plot. Because the log scale shrinks everything down, so the big ones don't stand out as clearly, but the other is a linear, this one is a linear plot and shows you that these are tiny compared to these really big events, but they're really big and they're really rare. You might say, well, what about something like Vesuvius and Pompeii and Vesuvius AD 79? Well, this is a very small eruption, okay? About the size of Pinatubo, 1991. And unfortunately, this was just a case of cities, Roman cities, towns being built right next to a volcano, wrong time, wrong place, and they got buried by pyroclastic flow deposits from these quite small eruption in AD 79. And of course, we're still digging out some of the buried parts of Pompeii and making spectacular discoveries about Roman life there. The other thing is that if we want to do any statistics to predict when the next big eruption might be, it's very difficult. It's almost impossible. Okay. Our best estimates are for a VEI 5 or 6 might be 1 or 2 every 100 years. For a step bigger, a VEI 7 or magnitude 7, 1 every few hundred years, probably. The small super eruptions of the size in New Zealand, about every 5,000 years, maybe. And then when you're up to the big ones, then 1 every 100,000 years or something. But this wouldn't stand any statistical tests at all, because the numbers that we know about in the past are very small. We know about very few of these events, and certainly not enough to do any sort of robust statistics. So if we work out an average global frequency, it may not be useful at all. You might, and you will see later, the dates on the eruptions from Yellowstone. Well, it's no use saying, well, there was one a certain time ago and another at a certain time ago and another, therefore the next one will be in the next few similar time period. It doesn't go like that. Volcanoes don't behave like that. So we have very little idea of what the time scale between these eruptions is. And we also have very little idea on the volumes, actually. And I'll use Pinatubo as an example. Pinatubo occurred in 1991. It's the best observed big eruption. There were satellites up there recording it from space. The Philippines was a country full of, there was a US military base near the volcano. It was very well observed. There were naval bases there. There was all sorts of instruments trained on this volcano. It erupted on June the 15th, 1991, formed a nice caldera about 2.5 kilometers across, seen here from one of my trips there. It produced thick pyroclastic flow deposits all around the volcano for distances of 15 kilometers away from the volcano. It had a ash fall that made it go dark at midday. This is a picture taken out of a window at Clark Air Base at midday. And as you can see, it's black. There's so much ash in the atmosphere. There's no visibility at all. This is the camera flash reflecting off pieces of pumice that are flying past the window in this. But we don't know much. We don't know a very good idea of the volume of this, even this recent eruption. The very reasonable volume estimates range from 3.5 to 5.5 cubic kilometers. Right? It's the second biggest eruption of the 20th century, and we still don't know its size precisely, largely because a lot of the ash fell at sea, fell into the China Sea. So this is a common problem with these big eruptions. The deposits are often at sea or very widely dispersed and now largely eroded away and not yet recognized. Oh, this is just a chatty picture. This is a group of students and people I took up to the caldera in Pinatubo in the year 2000. The main reason to show you is this chap here with the arrow pointing at him. He's Chris Newhall. He's the guy I worked on the Volcanic Explosivity Index with. So we took a group of students and people from a conference up to Pinatubo then. Anyway, we've got a fair idea of where these big eruptions might occur, okay? Because they're going to occur where the volcanoes are, and the volcanoes are largely around the Pacific Ring of Fire. We'll take a couple of views of this. These are large eruptions. So this is VEI or magnitude 7 in the last 200,000 years. Ka means 1,000 years. So this is the last 200,000 years. There've been a couple in New Zealand and some in Indonesia, and then various places, ones in Japan, I said, around the Pacific Rim of Fire. If you extend this to 1 million years, different looking map, but the same data basically. But if you include 2 million years, then you get an interesting cluster in Western North America, which wasn't on the previous map, okay? And you get a few others as well, like ones down in the Andes and over in a couple more in the the Mediterranean region. But because the longer you look back, the more you're going to get, but there really aren't many of these dots on this map. So let's look at a super eruption, and let's look at the biggest of them all, which this evidence has only been around for 5 or 6 years now, or maybe 7, that this event in Sumatra 74,000 years ago really is one of Earth's biggest eruptions that we know about. Okay, this is called the volcano is called Toba. It's this big hole in Sumatra filled with a large lake, and then it's got this block pushed up in the middle. And I will show you a picture taken standing on this block from the point where the arrow shows, looking down this part of the caldera in a few minutes. It's a complex caldera like Yellowstone. It's had 3 major eruptions like Yellowstone, and its caldera is as big as Yellowstone's. Okay, but it's only, I'll see the contrast in a minute, only 74,000 years ago, which geologically is very young. Here's a NASA radar image of the same area. And you can clearly see the big hole, 100 kilometers long, 40 kilometers across. You can see, interestingly, a giant strike slip fault like the San Andreas fault that runs right by the volcano all the way through Sumatra. It was this fault that moved, or some movement on this fault was featured in that terrible earthquake and tsunami in 2004 in northern Sumatra. On this flat land all the way around the coasts is due to the deposits, the pyroclastic flow deposits from this large eruption 74,000 years ago. It's just an enormous system. And as I said, this for size, this is 100 kilometers long from one end to the other. It's the result of 3 eruptions, but only one of them was huge, the most recent. Another one, its caldera is this part here, and then there were a couple of smaller ones earlier on in its history up here, but they've been totally swallowed up by the recent eruption. The dates on these are, there's about 1.2 million years ago, MA, about 0.8 million years ago for this one. There's another little one up here about 500,000 years ago, and then the big one at 74,000 years. And one of my questions about this system is, when you go there, there's nothing happening on the surface. There's no hot springs, there's no geysers, there's almost nothing going on to show that this is a very young eruption. Compare this with Yellowstone, and there's a lot going on at Yellowstone. You all know about Old Faithful geysers and the hot springs and the sinter terraces and everything. So it's a very different system. Here's my view looking up this east side of Lake Toba here. I'm standing on that block in the middle, and the arrowed is a tiny volcano. Looks tiny in the distance. That's actually 80 kilometers or 50 miles from where I'm standing. So it's just an enormous system, and I'm standing, I guess, about halfway along the caldera here. So it's a giant hole in the ground and huge deposits all around Toba. Okay, so let me go next. I'm not going anywhere.
Oh, Steve, we do have one question.
Yeah.
Yeah, Jyoti asks, how do you measure the past eruptions, as no one was there to tell us about them?
We rely on mapping the deposits from I showed you a picture, second slide, of the types of things that these volcanoes do, and they make ash fall deposits, and they make pyroclastic flow deposits. And people like myself go in, and it's a long, tedious process, but you have to map these deposits all around the volcano. And then you have to try and do age dates on them to prove that they're all of the same age. and then you gradually build up a picture of the eruption. There were people living in Indonesia and India at the time of the Toba eruption, but of course there's nothing written about that. They're early civilizations. And of course there's a big link between the ages of these eruptions and archaeology, because they're very interested in these ancient civilizations. And when an eruption occurs, you've got a time marker on the ground from the ash fall deposit, and archaeologists find these very, very useful for pinpointing the ages of things. So here's a map comparing. I've made the two maps at the same scale here. This is Toba and this is Yellowstone, and the big caldera Yellowstone is the one I'm outlining now. It's in red here. And when you work out the area enclosed in this and the area enclosed in this, they're approximately the same. Yellowstone's eruptions, however, were 2.1, 1.3, and 6.4 million years ago. So Yellowstone hasn't had any big eruption for well over 500,000 years, whereas Toba had one only 74,000 years ago. So Toba should be the much fresher, younger system, but it doesn't look like it when you go there. Yellowstone's a very active system with, as I said, hot springs and geysers and stuff. And there's almost nothing happening at Toba, which is really surprising. Anyway, here's a sort of cartoon of the ash fall, some of the ash fall from Toba compared to Tambora and Pinatubo, because Pinatubo is tiny, Tambora is a bit bigger. But this is a map of like probably 5-10 centimeter limit of ash from Toba. It covers India, Pakistan, up into the Himalayas. It's found all over Indonesia, and it's also found when they do coring of the seafloor in the Indian Ocean and the China Sea. There's more and more ocean exploration goes on, they find the Toba ash wherever they go almost. And so it was just a huge system. And a colleague in Italy, who was my postdoc for a year, of about 10 years ago, has produced a very nice study where he combined the known ashfall deposits from Toba. So the red dots are those on the sea floor, or you can see the ones on the sea floor. He combined that with some meteorological wind models for this region of the Earth and tried to predict what the size of this fallout deposit of ashfall from the Toba eruption would be. And he came out with a huge volume that nobody was expecting. and the total for this eruption is something like 5,300 cubic kilometers of magma. And this puts it on the level that's bigger than the estimates for the size of the Yellowstone eruptions. And it's bigger than the previously accepted largest eruption on Earth, which was 28 million years ago in what is now Colorado. After this paper was produced, there were a couple of articles that came out from archaeological groups finding the Toba ash in Lake Malawi here, and also near the southern tip of South Africa, of South Africa. So it kind of predicts that the Toba ash will be found over a large part of Africa, and it was. They have not yet reported any Toba ash in Australia, but this map or extrapolation of it would predict that it should be there in northwestern Australia as well. So it's just an enormous system. Well, let's talk a little bit about the atmospheric aspects of this. I use a very small eruption as an example. This is Mount Redoubt, 1990 in Alaska. You can see snow-covered volcano here, and it's produced a small pyroclastic flow. It's produced a couple, and from this pyroclastic flow has risen an ash column, and then the ash column has settled out in the atmosphere at different heights. So there were two large ash columns rose, and each settled at a different height. And so the ash is actually going up, gets into an area where the atmosphere around it is less dense than the ash column. So the ash column sinks back down and then spreads out as these spectacular umbrella clouds. And it's by this sort of mechanism, these then spread out with the prevailing winds. This is how gas and ash gets injected and transported away from these eruption columns. For a much bigger example, we just need to scale up the size of these. This is a very small system, and the Toba or Yellowstone would have a much larger system. So what we know about eruptions and their effects are based on the historic ones, of course. And as I said, we have only had very small events. Krakatoa, you might have heard of Krakatoa in 1883. Here I am at Krakatoa in 1979 or something. A little island in the middle was making small eruptions. It's now much bigger, and you see it on the web quite a lot. And because there were no colored photographs in those days, but the gas and what developed some of the gas put up into the atmosphere led to very bright sunsets. And the Royal Society hired an artist to go out and do watercolor pictures of the sunsets over London. So these are a series of pictures were produced showing the effects of the volcanic aerosols in the atmosphere over London when Krakatoa is nearly on the equator in Indonesia, so thousands of miles away. Okay. Well, what would a big eruption do? Well, there's a lot we don't know. As I was trying to stress, we don't know when they've occurred in the past. We don't really know when we might expect the next one. We don't have much idea of the true sizes, and we also don't have much idea of how much gas like sulfur and other gases will be released into the atmosphere, because there's a question related to the composition of the magmas that erupt in these and their sulfur bearing capacity, but I'm not going to go into that now. We do know that these deposits covered huge areas. We know something about the mass eruption rates because we've got some idea of the eruption duration. We have some specific case studies of big events like Toba and Yellowstone, but we don't know very many like that. And the one in New Zealand's been studied in detail. But we know the effects of small recent eruptions, but we really don't know whether it's simply a matter of scaling up to these bigger systems or not. So let me go here. The ash fall is fairly spectacular. This is this is an ash fall blanket made from a map. This is probably 15 years old, this map, from an eruption that took place near Naples, the neighboring volcano to Vesuvius, the other side of Naples in Italy. And it's 39,000 years ago, and its ash covers a large part of the Eastern Mediterranean countries and is being found further and further away from the volcano. If an eruption of this size took place in California, the entire state would be covered with a layer of ash for more than 4 feet thick. Or there's a no comment now. Okay, 1.25 meters or 4 meters thick. And this is a map of the Yellowstone ash falls superimposed on the western half of the United States. So the eastern border of the map is the Mississippi. It's Texas here, Baja California, the California coast, Canada, the Canadian border, and these colored shapes are the three ash falls, or 2 ash falls from Yellowstone and 1 from the supervolcano in Long Valley, down in the eastern part of our state. And as you can see, if one of these occurred, the whole of North America would be covered with ash. Canada too. These are probably, unfortunately, the guy who made these maps died, and nobody knows the limit of the ash fall represented by these maps, whether this is 5 centimeters or 2 centimeters, but you can bet your bottom dollar that the ash fall would actually be wider than these areas shown. So from one eruption, you could sprinkle ash all over the United States and considerable portions of Canada, Mexico, and everything as well. So really quite an astonishing thing. And you don't need much ash to do damage. This is after Pinatubo, 3 centimeters of ash falling on buildings at Clark Air Base. Unless they went and swept it off the roof as it was accumulating, then they got a lot of roof damage, because roofs aren't made to protect from ash. They're made to protect from water or snow, but ash is 2.5 times denser than water or snow. And therefore, also airborne ash is an aircraft hazard. I can talk about that later. So if we're predicting these ash clouds would be in the atmosphere for weeks or months, maybe, then it's a disaster for air traffic, as we had a little event in Iceland in 2010 that demonstrated that. On the ground, it's a respiratory health hazard, and ash on the sea surface may have very profound effects with algal blooms, and also with the ability of the ocean to absorb carbon dioxide and things like that. So there's a lot of things are tied up with the effects of widespread ash fall. I'll just say a few words about the gas effects. When a volcano erupts, it puts carbon dioxide and sulfur dioxide into the atmosphere. The sulfur dioxide combines with water in the atmosphere to make sulfuric acid. It's in the form of an aerosol, tiny particles, aerosol cans, spray, tiny particles. And these reflect and absorb the solar radiation. They also reflect back some of the longer wavelength radiation leaving the Earth's surface. But the net effect of this is that the surface cools. And therefore, after these eruptions that produce SO2, we may have years, several years, 3, 5, 4 years of very unusual weather. They also affect precipitation as well. And there's a lot of studies about this, and relating the effects of these super eruptions on the Earth's climate has proven difficult, but most people believe that there would be a severe effect, at least for a period of 5 to 10 years after one of these events. I'll stop there. This is a shuttle picture, photograph from the space shuttle of the Pinatubo aerosol cloud. I'm not sure how long after the eruption, but you can see clouds at the top of our lower part of our atmosphere. This is the cloud-free stratosphere of the Earth. And you can see this dirty gray layer. There's a couple of layers here, which is the actual particles of aerosol in the atmosphere as seen from the space shuttle. We've had, we know from historic, it's nearly finished now, we know from historic accounts some of the environmental effects of the biggest eruptions we've had historically. But as I've underlined, these are pretty small, really. Okay, so there was an eruption in 1815 from Tambora in Indonesia. The aerosols went up into the atmosphere. And in 1816, people have pieced together, I've been part of this work years ago, piecing together the effects of this event on the climate on Earth. And there's a few capsulated bits here. In England, many tens of thousands of people died. Ireland had a famine. In Switzerland, there were food shortages. In France, there were food shortages, which has political ramifications. London, it was cooler than usual. In North America, particularly, it was called the year without a summer, and all of the crops froze in July and things like that. And they helped to lead to the great expansion of people to the Western United States, looking for a more climatically reasonable area. And there's a book written about this, The Last Great Subsistence Crisis of the Western World, by a guy called Post, published 1985. But it's quite a well-known event in social and economic history for this, the effects of this eruption. And an artist like Turner in Britain were collecting sketches all through this post-Tambora period, and I'm pretty sure that he combined them into some of his amazing turgid skies that you see in his pictures. He's not the only artist to do this, because they didn't have cameras then, but art may well provide us with a way of visualizing what the effects of the atmospheric aerosols would be. And we could look forward to many years of this, perhaps globally, from if we did have another super eruption. Okay, so what would happen? Oops. We'd get sudden changes in weather and climate. There will be ozone depletion. I haven't talked about that yet. Reduced light levels because the aerosols block the sunlight coming through. Food shortages, air and water quality issues on a very wide scale. Air and other transport and communication disruptions, because you wouldn't be able to fly aircraft, and we're not sure how satellite-borne instruments will perform looking through a global aerosol cloud. And there's many more. There's more things than we can even think about that we haven't really envisaged. So thank goodness these eruptions are very, very rare. And I swear that even our grandchildren's grandchildren will probably never have to live through the next super eruption on Earth. And I'll usually get the question, where do I think the next big eruption will be? And so I'm answering it here, maybe trying to predict this question. But my pick for the next big eruption on Earth, it might surprise some of you, is in the Philippines. It's not Pinatubo, because it's a tiny system. It's this volcano called Taal. And it's just south of the Manila region. There's something like 30 million people living in this region of the Philippines, Manila being a very large city of approximately 20 million people. And there is this caldera volcano here, and it's got a history of, I don't know, 30 or 40 eruptions since the 1600s. It's actually been erupting. It erupted in 2020. It erupted in 2021, and there was a little eruption at the beginning of this year that didn't get reported. So it's obviously a volcanic caldera system that's alive and well and erupting nearly every year. It erupts through the main crater on the island and the little volcano in the middle of the caldera. But what I'm worried about is this escalating to a much bigger caldera forming event. And so we've had a colleague and a student have been working on Taal and trying to puzzle out how old its previous big eruptions were and things like that, because there's almost zero knowledge about this large volcano. So that's my pick for the next serious eruption on Earth. I'm not saying it's going to be super eruption size, but it might be a very surprising event if it occurs. Okay, that's it. Thank you very much for listening. I hope you've learned some things about the large scale eruptions, and please ask some questions. We have any more on chat? Let me check.
Yeah, Alan has a question. Alan, why don't you
Yeah.
unmute and ask your question?
I'm just wondering, do these eruptions tend to be from volcanoes that have larger lava chambers beneath, or do we know?
We presume so. Okay. I don't know if I can get this back. Yeah. The caldera is assumed to collapse into the magma chamber, right? So if you think of the caldera as being roughly the footprint of the magma chamber, then the answer to your question would be yes. But of course, you know, it's a little more complicated than that. You can see these lovely scallops that occur in nearly every caldera. Well, these are due to landslides into the void that is formed after the magma chamber empties. And so the actual, you know, the actual footprint would probably be, well, will be inside this, not quite as big as the caldera area shows. but the answer to your question would be yes. The big question is it all at one level? Is it all at one level in the crust of the Earth, or the lithosphere of the Earth, or is it like multiple levels that are sort of connected before the eruption, and once it sort of falls into one level, then it can go down another level as well? But that's a question that's a lot of research being done on, but that's a good point worth bringing up. The simple answer is yes, big magma systems. It might be worthwhile adding to that as we've never had one of these occur in our modern societies, we have no real idea of how long there would be signs of a buildup before the eruption. We're pretty sure it's not going to suddenly become active and have a huge eruption over a period of a few weeks. But some people have proposed it's as short as a few years, and others say, oh no, these magma systems, they've got to show signs of activity as they're building up, and we'd have centuries of unrest at the volcano. But we really don't have much idea of how quickly one of these eruptions could be released upon us. So something to be borne in mind there.
I have a question. I would like to know, there's a lot of talk about earthquake predictions,
Right.
and how that science is in its infancy. And
Yeah.
I hear you speaking about how there's not currently a lot of knowledge about volcano predictions. Is there a relationship between the two, prediction-wise?
Yes, I think we have to say yes. But for instance, when the Sumatran earthquake took place in 2004, there were several volcanoes, there were several volcanoes on Sumatra that became active very soon afterwards. This isn't written about much, and it tends to be a bit fringy still in geology and volcanology. But the Pinatubo eruption, here's Mount Pinatubo on the same slide as I was just talking to, and it's about 150, 200 kilometers south of Baguio, a city in the Philippines on Luzon. And 9 months before Pinatubo erupted, there was a magnitude 7.2 earthquake near Baguio on a fault that actually extends from near Baguio down to by Pinatubo. And so several people think that the motion on that fault and the big earthquake actually stirred something up in the magma chamber underneath Pinatubo and set a cascade of events going that eventually led to the 1991 eruption. So I fully believe that the answer to your question is yes, but you might not get that if you took a sort of survey of what's written in the geologic press. So good question. Now, there was a lady with a question.
Yes, Sarah.
Yeah.
Sarah.
Hi, Steve. It's great to hear your talk today, and again, to expand our knowledge on this. On your list, besides Taal, you show Naples, Long Valley, and Yellowstone. Are the events that we do observe at Yellowstone hopefully taking pressure off that area, or are we likely to see something more exciting happen in that area?
Right. Well, let me just take a step back. The Naples region is that one that I showed a picture of the ash that went all over the Mediterranean. Okay, that's a caldera system to the west, just to the west of Naples. Long Valley, I think we can forget. because since I made this slide, a guy has published a paper saying he thinks the big magma system at Long Valley was a sort of one-off large eruption and won't become active again. He's got a pretty convincing story for that. And with Yellowstone, I mean, I think it's just what one of these volcanoes does in between its big eruptions. And as the eruptions are hundreds of thousands of years apart, there's plenty of time to do this. And so it will create hot spring deposits, and the hot springs will move from place to place. It will have geysers. It will keep going. And I just think that this is just sort of business as usual for these big caldera systems. The one by Naples does exactly the same thing. It just happens that when I went to see Toba, I was shocked at how little was going on in Toba. I hadn't even thought about it till I got there. But Toba is so young. Why isn't it like Yellowstone, or even more bubbling and more geysers and things like that? There's something weird going on about Toba that I don't yet understand. But I would just say it doesn't mean that it's taking pressure off Yellowstone, because I think there's there's no evidence that Yellowstone is building towards another eruption. It's just in the pause between big eruptions. And well, that's what the experts on Yellowstone are saying.
Thank you. Thank
yeah,
you.
but they're not like, people talk about, well, if fault moves, that's good because it's taking the pressure off for a big earthquake. But I don't know if that applies to these volcanic systems like that. Okay.
Audrey.
Hi, thank you for speaking to us. It's been very clear and appreciate it very much. I was wondering, are big communities like Manila or Tokyo or places like that are in line to get a big eruption? Is there anything that they can do physically to protect their population? Are they doing anything like that? I think some small communities can, but maybe not big ones.
Yeah, very good point. Small communities can, because of the involvement of the US military, or not only US, but the US, Philippine, and other nations' military installations in Subic Bay and next to Pinatubo, and because we sent a team from the United States Geological Survey out there, led by Chris Newhall, the guy I worked with years ago. They managed to persuade the Philippine authorities that there was going to be an eruption. It was going to be severe. It was going to be, just in the area of Pinatubo. And so they moved tens of thousands of people. It was a huge undertaking, but this is if you like, what you've just mentioned, a small community, and it was successful. Very, very few people actually died. But imagine doing that for something like Manila or Naples. Right? The only thing you can do is to evacuate people and try to save lives.
Mm-hmm.
That's really the only sensible thing to do, and then trying to evacuate a major city. I might add here, to me and to Chris Newhall, who now lives in the Philippines, he's married to a Filipina, we are very concerned because the Philippine government has designated this area here as its sort of major area for industrial and high-tech development. And it's promoting all sorts of growth. There's new towns sprouting up all around here and everything. Totally in disregard for the fact that there's this active volcano here. So, and this thing here, this weird three-fingered lake, is also another caldera volcano. At least the middle part is a caldera, and we know almost nothing about this. It's a little older than Taal, and we know nothing about it or its eruptions, or almost nothing. Okay. But to me, it's a very volcanically dangerous area, and to stake your country's sort of future economic development on infrastructure in this region doesn't make any sense at all. But unfortunately, that's what they've done. But it's lovely, flat, sloping land from the edge of Taal caldera down to Manila Bay. And the reason it's lovely, flat and sloping. For development is that it is the top of the pyroclastic flow deposits from Taal caldera. So our colleague in Britain has just had a grad student do a PhD on this system, looking at these bigger eruptions, and we're hoping to get some age dates on when these events took place in the past. But right now, we have no information. Yeah.
Roger had a question.
Oh, yeah. Hi, thank you. As a follow-up on Audrey's question about what people can do, when we were in Japan, we went to Hokkaido in the North Island, and there's active volcanoes there.
Right.
And we went to one town where it was a small volcano, but up on the flanks, they had built walls that they claimed could divert the flow of lava and protect the town.
Yeah.
And I was flabbergasted. I didn't think anything like that could ever work. Do you think that would work?
I've also been fortunate enough to spend some months on Hokkaido, and I think I've seen what you mean. These are built, there's a name for them, and I can't remember what they're called. It's a Japanese word. These systems, the Japanese lead the world in this. They're built not only to divert lava, but mainly to divert mud flows, lahars or mud flows, which are much more common. And so they're meant to protect the towns from being overrun by mud flows, and I think they will work. The big problem with lava blocking, and it's been tried in Hawaii very long ago, and not really very successfully. It's been attempted in Italy. The problem is the lava is going to go somewhere, right? If it goes where it will naturally, it's an act of God. If you've diverted it and it goes onto your neighbor's land, then your neighbor can sue you because you have changed the act of God. And so then it falls into the realm of insurance and legal matters. And so people have tended to steer clear of doing that in several countries because of this reason.
But in some cases, it could actually be helpful.
Yeah, yes, it could work. You could divert a flow, you could divert a lahar. Yeah.
But it would depend on what type of flow, I suppose. If it was a pyroclastic, the thing it's mostly airborne.
A pyroclastic flow, because part of the flow is less dense or about the same density of air as air, it would just go over those things like they weren't even there. They'll be very, you wouldn't be able to stop much of a pyroclastic flow. It wouldn't be much of a system. But if it's a lahar producing or lava producing volcano, then those types of, what's it called? It's something engineering they call it, and I forget the name now in whatever it is.
Okay, thank you.
Yeah. There was a lady who looked like she was going to answer a question, but I've lost her. So not there.
Oh, Iowa, Noah?
Yes.
Yeah.
There you are. Her voice is off.
Unmute.
You're muted. Unmute. Send her a message. Oh.
There she goes. Hey.
Yes. Hi.
You're muted again.
Oh. Yes, she muted again.
It doesn't want. Come on, get off there. Yeah.
There you go.
I got it. Thank you so much. This has been such a great discussion. I was just curious in what extent that has on the sea life that's around there and how far it extends.
Sorry, you're talking about sea life?
Yeah, when it goes down to the sea, go down to the water.
Right.
Like in Hawaii.
Yes. Well, I think that's something that's more or less unstudied. Uh, we know from history, and we know from more modern observations that a lava flow will go down to the sea, and it will largely break up as it enters the ocean, and the effects of the lava flow going into the water are pretty localized. And presumably marine life and things can move away.
Oh, great.
Well, we also know that when a pyroclastic flow goes into the ocean, part of the flow is denser than water, and part of the flow is less dense than water, and therefore, sorry, my screen's decided to go crazy. We don't know the effects of the pyroclastic flows underwater. Presumably, if there were coral there, it would just get buried. But we do know that at Krakatoa in 1883, pyroclastic flows went across the surface of the ocean and hit and killed people in Sumatra, 40 kilometers. So that's 25 miles away. So they traveled across the top of the ocean for 25 miles and were still able to be hot enough and erosive enough to actually do a great deal of damage. And people have got small examples of small events like this. There was an eruption in the late 1990s into the early 2000s in Montserrat in the West Indies. And that produced some pyroclastic flows that went into the sea, and people have photos of these pyroclastic flows going across the sea surface from them. But it is an area that really sorely needs study, as is the effects of ashfall on ocean surfaces on a large scale. Very good question. Thank you.
Thank you.
There's something funny with my computer. It's sort of flashing on and off. I'm sorry if you're seeing, I don't know what you're seeing. I'm sorry, but
I can stop sharing.
yes, I'll just do stop sharing. There we go. That's better.
Oh, there we go.
Okay.
Any more questions?
Steve, you mentioned at the beginning Tonga, and you might have a few closing comments on that.
Right. Yes. There is a volcano as part of the Tonga Islands. The one in particular is called something like Hapatonga or something. It's got anyway, it's largely a submarine volcano, but the little bit of the crater rim at the top sticks up above the water. Okay. And in January of this year, there was an explosive eruption from this volcano where the explosion wasn't deep enough to be totally affected by the depth of the ocean. And so there was an explosive event into the Earth's atmosphere. And this eruption defied anybody's in my field's predictions of how it would behave. The eruption cloud went much higher than anything our theories and our observations have predicted. And we think it did it because it had so much seawater vaporized by the eruption. And this has led to a whole series of papers appearing very quickly in the scientific journals about what happens when you suddenly inject a great deal of water into the Earth's stratosphere, which is normally dry. So the stratosphere begins at about where we are at about 13, 14 kilometers height in summer and lower in winter. And down around the equator, it's about 17 kilometers. But when we fly in a jet aircraft and you reach cruising altitude and you look out the window and it's blue and cloudless above, you're looking into the bottom of the stratosphere there. So, but this plume went right through the stratosphere and into the mesosphere. 52 kilometers it's supposed to have topped out at. And so this is astonishing. I wouldn't know how to classify this on the Volcanic Explosivity Index. It's something totally new to our field. So that's what I would have said about it. And that's this year, January 18th, I think, or 15th this year this occurred. So we're still learning a lot of things about volcanoes that we never knew or had very little idea of before.
And we continue to get earthquake reports from USGS constantly from Tonga. So it's still rattling around.
Oh, yes, yes. It's had several eruptions in previous years. And I really think that everybody realizes this is not the last we're going to hear from this volcano. So, yeah, good point. It also triggered, it produced a huge shock wave in the atmosphere, and the shock wave was coupled to the sea surface, and it produced tsunami in other oceans rather than the Pacific much earlier than they could ever get there by being propagated through the bodies of water. So there were tsunami measured in the Atlantic much quicker than they could have ever got there by any sort of ocean-bound route. And they were tied to the shock wave moving out from this volcanic explosion, causing the sea surface to ripple, and changes in sea level at places where which are measuring water levels around the ocean basins. That's another very interesting thing. We've known about that since Krakatoa in 1883, because it was recorded then, but not much work's been done on it. But now, of course, there's a huge interest. Now it's happened in modern times. Oh.
Any other questions out there? If not, I would just, Steve, thank you very much for your second presentation to us. Bravo.
Thank you.
And
Thank you very much.
You're more than welcome to attend any presentation in the future.
I will try.
Oh, good.
I will try and attend and please send me the emails that the presentations are when they're happening.
You were on the list, and should you come up with a new topic in future years, feel free to let me know. We're always looking for new people.
Okay, thank you. Thank you.
Thank you.
Too much self-exposure is not a good thing, though. So there we go.
There you go.
Okay. All right.
Okay, thank you again from all the members.
Thanks. Sorry for the scratchy beginning. Thank you.
Thank you.
Thank you very much.
Bye.
Bye, everybody.